My name's Russ. Thanks for coming here today. And I'm going to tell you about how we've built an open source communications layer for the metaverse. And I think an important way to start is by asking what actually is the metaverse, right? Apparently the metaverse is dead. Well, I think maybe the metaverse with a capital M is dead. But what's the metaverse with a lowercase m? I love this take from Sean a couple years ago. He asks, what if the metaverse isn't a place that we go to? What if it's not the Oasis from Ready Player One or Horizon Worlds, but instead it's a moment in time? Kind of like the singularity is for AI. What if the metaverse is a moment in time where our digital life matters more to us than our physical one? And what if we've been building towards that moment for the last century? 100 years ago, there were no screens in your life. All of your attention was focused on your physical environment. When the television came out, that dropped to 85%. When the desktop happened, 70%. When you started carrying a mobile phone in your pocket everywhere you went, 50%. It's only a matter of time before somebody, maybe it's Meta, maybe it's Apple, maybe someone else, before someone creates computers that you wear in front of your eyes, that comfortably sit in front of you, and at that moment, 100% of your attention, or at least part of it, will be on a screen. And Sean thinks that that is the moment where we will cross into the metaverse. And if you believe him, that the hardware is only a few years away, well, what about the software? What kind of software infrastructure is going to be needed to help application developers build for that future? I think the answer is actually found by looking back just a few years. You see, we've all already been in the metaverse. That's my hot take. And that was the lockdowns of 2020. For some, a year long. For me, 2 years, maybe in some change, where pretty much everything that I did in the offline world shifted to be done online. So I had friends that had their first dates on the internet. I was watching YouTube videos trying to figure out how to cut my hair, which clearly I did not succeed. But I was learning how over the internet. Heck, I actually attended 4 weddings over the internet in 2020. And like a wedding, the most fun possible thing you could do in the physical world, I'm now doing over Zoom. And so for all of these activities, these were the types of applications that made it possible. Some of them have existed before the pandemic, like Zoom, and other ones like Gather or Clubhouse were born and motivated by this new world we found ourselves in. And if you look at all of these applications and what they needed to do to move life online, there's a unifying thread amongst all of them. They were all real-time, synchronous in nature, and you engaged in them and interacted with them with people that you knew, sometimes people you didn't, but with other people. So they were multiplayer. And almost every one of them used your camera and your microphone to capture your identity, your presence, and project it from the physical world into the digital one. And so how did they do that? They used a technology called WebRTC. Web Real-Time Communication is the name of it. And unlike HTTP, which powers most of the web, WebRTC is designed for real-time low-latency data transfer. HTTP is a protocol built on TCP, and it's made for really transferring hypertext, text, over a network. WebRTC, on the other hand, is built for media transmission, high bandwidth data like audio and video. And like HTTP, it's available in every browser, even on mobile phones. The problem with WebRTC is that it's actually really hard to use. David and I, David's right there, David and I, we were working on an application during the pandemic with a goal of actually connecting people in this new online world that we were living in, just like those other apps I showed you. And we ended up building our own stack for dealing with and working with WebRTC. At a certain point, we decided, what if instead we build a company and an open source project around making WebRTC easier to use for developers so that they don't have to go through the same pains that we did. It's been 2 years since we had our first release of LiveKit in open source, and it's amazing to see that some people who build apps that I have on my phone and I use every single day are using this stack for building real-time features. And the way that we make WebRTC easy to use is really by just solving all of the problems that it has, starting with its ergonomics. If you've ever worked with WebRTC before, it's frickin' complicated. You can see this diagram on the right here. This is just the basic call stack that you have to go through in order to get one person to start sending their audio and video data to another person. I'm aging myself a bit here, but if you've ever built payments processing with PayPal before Stripe existed, that's kind of what it feels like to use WebRTC before something like LiveKit existed. And so once you start to kind of get deeper into WebRTC, you build an application that's starting to run at scale, you have to look into things like weird firewall issues that a user may have, or adding security on top of it, or performance characteristics of your WebRTC sessions. And that's when you learn that WebRTC isn't a protocol, it's actually a collection of 10 protocols that have to interact with one another, and you have to kind of become familiar with all of them to really be effective. So the first thing that we do is we take all of that complexity, all the acronyms, and we tuck it behind just 3 very simple high-level concepts. The first one being a room or a session. You can think of it as a stateful container, something that represents people getting together into a space. The second thing is a participant. So a room or a session can have 1 or more participants in it. And the third is a track. So a track represents a stream of some kind of data, and a participant can have 1 or more tracks. A track could be your camera stream. It could be your microphone data. It could be an audio file if you want to build a live DJing application. It could be a movie file if you want to have watch parties, build an experience for watch parties. And after we have those kind of 3 primitives established, you can compose them in any way to build your real-time app. And that's kind of where we stopped when we made our first release of LiveKit. The thing that we didn't want to do, especially in the context of building infrastructure for the metaverse, is we didn't want to assume that we knew all the different ways that someone might want to integrate real-time audio and video. We didn't want to build a specialized framework for video conferencing, because that's just one of the 1,000 different ways that you might use this technology. And so what we did was we put out this very kind of minimal stack and said, let's listen to the community and figure out what kinds of things are people going to use this to build, right? And so things like when a bunch of developers started to ask for spatial audio or text chat or being able to record sessions, after enough people ask for those things, they become undifferentiated problems, something that every developer is now having to build themselves from scratch. And those are good candidates for us to take, build into our core API, and make it available to everyone else. What that means is that for a use case like video conferencing or spatial computing or robotics, you can actually build those applications with less code than you did before. But if you're building something brand new, you can drop all the way down to the lowest level, which is what we designed for in the first place, and build your app. So now that we've got the ergonomics right, and kind of like that client interface, the next problem to solve is around scale. WebRTC, by design, is a peer-to-peer protocol. And what that means is you've built the signaling layer yourself, and now once the session is established and you have to forward media, that media travels from point to point directly without any intermediary. So the way that works is if I'm in a one-on-one call with you, what's your name, by the way? Kush. If I'm in a one-on-one call with Kush, Kush is in Vancouver, and I'm in South Korea, we are actually exchanging media directly from Vancouver to South Korea. Now, and your name is? Rotvik? Rotvik and Kush. So if Rotvik joins this call, now there are 3 people in this call, and I'm sending my audio and video out to 2 people. And you're sending your audio and video out to 2 people as well. If David joins this, and now we have 4 people, I'm sending it out to 3 people, and so on and so forth. For n people in a conference, you have to send out n-1 streams in peer-to-peer WebRTC. How many home internet connections do you know that can upload 10 simultaneous HD video streams at the same time? Pretty much none, right? So we need to figure out how to increase the scale. In practice, peer-to-peer WebRTC only scales to about 3 to 4 people in a session. But if we're talking about building metaverse scale applications that have potentially thousands of people interacting in real time, we need something else. And so the first step here is vertically scaling WebRTC. The way you can kind of conceptually think about this is we take that signaling, that centralized signaling server we had before, and then we fold the media routing elements directly into it. What we've effectively built here is a centralized super peer that sits in the middle that speaks WebRTC as if it's any other peer in a network. And so with this super peer here in the center, you have these 3 clients, and from their perspective, they're just doing a one-on-one call with that central server. The central server here, or the SFU as it's known, is responsible for all of the hard work. It's taking these streams, it's figuring out how to triage them, whose bandwidth can handle which frame rate or which kind of resolution, and then forwarding those streams along based on that information. So it's doing all of the heavy lifting here. LiveKit built its SFU completely from the ground up in Go. And the reason that we chose Go, there were a couple reasons that we chose Go. The first one is that Go is designed for high concurrency IO-bound workloads. It's kind of perfect for the type of application that we were developing. But more importantly, the second reason that we chose Go is because of the Pion library. And so Pion is probably the most mature, kind of well-used server-side implementation of the WebRTC protocol, and it happens to be written in Go. If you compare what Pion offers versus the traditional WebRTC application, libWebRTC, which runs in browsers, Pion is specifically designed for the server side. With client-side WebRTC, you need to, well, WebRTC itself will decode those streams, presumably because as a developer, you want to render them in a browser or another device. But on the server, you don't want to actually decode those streams. If you decode and re-encode streams, there's a big performance hit that you take both on CPU, and there's a potential latency implication as well. So Pion is specifically built to facilitate server-side WebRTC apps, which our SFU is. A second thing that I think is important about LiveKit's SFU is that it's based on an open signaling protocol. Now, LiveKit is completely open source, but when I mean that it's an open signaling protocol, it's that you don't have to trudge through our code to try to piece together how our protocol works. The entire thing is declaratively specified in protobufs. So you can look at our protobuf file, and you can figure out what messages are going back and forth between our client and server. And because protobuf basically universally supports every compilation target, you can just target whichever platform you want and bring our protocol in. And we have a couple of frameworks in non-Go use cases that have taken our protocol and integrated it. And so now LiveKit, 2 years on, has been deployed by thousands of companies and projects on pretty much every cloud that you can imagine. And from a single server, we've been able to unlock 2 to 3 orders of magnitude more in scale from the traditional WebRTC architecture. The tricky thing is, well, this works for 80% of applications. But when we launched LiveKit's SFU, some developers asked us for even more scale. Could we unlock 2 to 3 more orders of magnitude from where we already were? They really wanted to build applications like this. They just play through the whole song, so I'll just go forward. And so if you're not familiar, that's Fortnite, and that was the BTS concert that they hosted in Fortnite a few years ago. Just to get an idea or a reference, that event did 50,000 people simultaneously in that single concert. So that presents some challenges. Being able to pull off that kind of scale from a single SFU just isn't going to work. And it's not going to work for some reasons here. The first thing to kind of notice about LiveKit's SFU is that it's a single home architecture, like every other media server. What that means is the SFU, well, a WebRTC session can only be hosted by a single SFU, so running in a data center somewhere. If I have that SFU running in Tokyo, and I'm in South Korea again, and I'm talking to someone who's in Vancouver, that person from Vancouver is forwarding their media to Tokyo. I'm forwarding my media from South Korea to Tokyo. And then if someone from Germany joins, they're forwarding their media from Germany to Tokyo. Now, South Korea to Tokyo, no big deal. They're pretty close. But from Germany or from Vancouver, it's quite a distance to go, right? And there are latency implications to doing that. The other problem with the single home architecture is that it's a single point of failure. So if that server fails, and trust me, it will, a lot, how do you resume that session? It's unclear how you do that without disrupting the user experience. And the third key reason of why there's a problem here with unlocking scale is that even in a 50-person conference, right, where you're sending your video stream out to 49 other people, that's already going to tax or hit upon the I/O limit of most network links in a data center. So, even though you can get a beefier and beefier machine, a 32-core, 64-core, you're really kind of at the mercy of that single box's resources. And so that required us to unlock that next 2 to 3 orders of magnitude in scale. We had to think beyond just vertical scaling and start thinking about horizontal scaling. The tricky part with horizontal scaling is you're no longer kind of deploying a server somewhere in a data center. You're now operating a globally distributed network where all of these servers have to coordinate with one another. And so we made a decision to build a new product on top of LiveKit's SFU, which is a cloud-managed network of our open source SFUs called LiveKit Cloud. And when we were building LiveKit Cloud, we had some design constraints that we wanted to meet. The first one is that it needed to have global low latency to every single user. So if you were connecting from Tokyo, or if you were connecting from South Korea or Germany or Vancouver, you were only 100 milliseconds from the closest edge. And then once you hit that edge, all media is transported over the private internet backbone. The second thing that we needed to support was we needed to support massive horizontal scale. So any session could support 100,000 or more people in one single session. And the third thing we wanted it to be hyper resilient. So I was talking about that single point of failure earlier. In cloud, one of the things we learned is that a node can fail, a data center can fail. In very, very rare circumstances, an entire cloud provider could fail. And so we didn't want any point of failure in this network. So we had to deploy across multiple clouds at the same time, treat them as one network. If any node or data center went down, users could be transparently just moved over to another node without them even knowing that there was a service disruption. And so we with the cloud design, it's designed as a global mesh network. In some ways, you can conceptually think about it as merging together the SFU design with the WebRTC peer-to-peer design. Right? Any single data center itself is kind of server control coordinated WebRTC, and then it meshes those streams out to other data centers around the world, and then ultimately other participants too. The last and probably most important design constraint that we had when building this was that it had to use the exact same SFU, the exact same SDKs, and the exact same APIs as LiveKit's open source product. And the reason for that is we wanted developers to not be locked into LiveKit Cloud. We wanted you to be able to move between self-hosted or cloud-hosted without changing a single line of code. And it had to use the same SFU because every improvement that we make to the core SFU flows back into open source and benefits cloud at the same time. So now that we have developed kind of a really nice interface, and we are able to scale from 1 to 100,000 or more people, the last thing left is really, on the client side, how do we get that client or developer interface on more platforms? So how do we scale the client, so to speak? When you're building for the metaverse needs to be available to everybody anywhere that they are. And what that means for us is that we need to be available to every developer no matter where they are, on any platform that they're building on. I think when we launched open source, one of the reasons why we ended up growing so quickly was primarily because we launched on a bunch of platforms right out of the gate. So we had React support and JavaScript and TypeScript, and we had Swift support for iOS and Mac, and we had Android with Kotlin. And I think what was interesting about that from the community standpoint was that even commercial companies didn't have mobile SDKs for WebRTC at that time, right? So how does an open source company have that out of the gate? But over time, as developers asked for Flutter support and React Native support and things like that, it started to become a bit of a liability. The first reason it's a liability is just due to differences in WebRTC implementations. While everybody pretty much takes libWebRTC and wraps it, each of these platforms makes certain changes or customizations that aren't always the same. Even between the browsers, so Firefox, Chrome, and Safari, there are differences in how libWebRTC is integrated into those binaries. In Chrome, for example, it treats the number of audio elements that you have differently from the way Safari does. And Safari has restrictions around how audio works on mobile Safari. If you extend that to native platforms, on Android, there are limits to how many videos you can decode. And on iOS, there are limits to how many audio streams that you can decode. So there are all these little differences that you either have to patch or hack around or have polyfills for. So it becomes quite tricky just from kind of the bare WebRTC level. But then on top of that, from like a developer standpoint or how we kind of internally operate, every time we got requests for features like moderation or screen sharing or spatial audio, we're having to build those things over and over and over across all of these different platforms that we support into all of these different SDKs. So, it's not dry. We're repeating ourselves all over the place. The tricky part related to that is that each platform does have unique features that we don't control, that are maybe baked into the operating system. So things like the way that events are handled, or how screen recording is done, or how you access the hardware, the raw kind of camera and microphone. Those things tend to be different across these native platforms. And so that's another thing that you do need separate code for, and you can't really abstract it out. And then, of course, all of our teams that work on our SDKs, they operate independently. So certain SDKs have features that other ones don't. A lot of compatibility challenges here, but there was rather a benefit to us doing this, right? There is a silver lining, and that is by building these bespoke SDKs across all of these platforms, we learned really, really well precisely which code was an undifferentiated problem and which thing was bespoke and needed to exist for that platform. So we knew kind of where to make those surgical incisions and cuts. And so when we started to work on cloud, we also spun out a separate parallel project, which was to build a common core, one core to rule them all. Could we take all of that undifferentiated client code and abstract that away into this core SDK that everything can kind of be built on top of? And so the first question to answer when we were designing and building this core SDK was, are we going to use C++ or are we going to use Rust? C++, of course, because it interoperates with libWebRTC. libWebRTC is written in C++. So it'll be a nice, clean kind of calling interface there. Rust also is an exciting language, but it's interoperable with a whole number of languages, which is what made it attractive. We ultimately chose Rust for a bunch of reasons. After doing a bunch of kind of research and debating back and forth. So the first reason is clearly Rust's unique ownership model and the way that it does thread safety. That was going to lead us to, as the amount of code that we write grows, that was going to lead us to less error-prone code over the long term. The second reason is that kind of build configurations using crate are much easier, or at least a bit easier, than the kind of diverse ways that build toolchain that you have for C++. Rust, of course, is a more modern language, so it is a bit nicer to write, even though we do love C++. And then there's a rich ecosystem of tools that you have available to you in Rust. So things like WebSockets, async executor, those things are kind of just there and a crate away from being leveraged. And lastly, while we aren't doing anything with it yet, it is nice to have that WASM target available to us so that we can target kind of the web platform through this core. The second question to answer after we decided on Rust was, well, are we going to use libWebRTC and call into C++, or are we going to use a pure Rust implementation of WebRTC? The reason that we went with libWebRTC over the latter is because libWebRTC, as I mentioned before, WebRTC-RS is a Pion port. So it's a port of Pion in Rust. But by being a port of Pion, it's also specifically designed for server-side WebRTC. What we're talking about here is building a core for client SDKs. And so libWebRTC is specifically designed for client-side WebRTC. So it was definitely the more prudent choice here. But it wasn't the only reason. The other reason is that it's been running for a decade in Chrome. So it's extremely battle-tested. We kind of know what we're getting ourselves into. And then the third reason is that we are the maintainers of our own WebRTC distribution, effectively a customized version of it. And now larger companies as well have adopted it as their WebRTC distribution too. In that distribution, we have patches for things like end-to-end encryption support, memory leaks, hardware decoder fixes, a whole manner of things. So being able to leverage that across all of our different clients was going to be valuable to us. Once we had a very kind of clear set of answers to those design questions, this is what ultimately became our Common Core architecture. So the whole foundation is kind of built on LiveKit's distribution of WebRTC. And then we have a binding layer to Rust using the CXX crate. But, before I forget, Theo, my coworker who basically designed and built this entire thing, he did want me to shout out David Tolnay from the Rust community, who's built a ton of things for the Rust ecosystem, and we leverage a bunch of those in our code. So thank you, David. And so CXX provides this crate, which is a binding to the Rust core itself. Within the Rust core, we start with a layer called WebRTC sys. That's effectively a direct one-for-one Rust wrapper around the APIs that we use in C++. And it's an unsafe wrapper. LiveKit WebRTC is the next crate that sits on top of that, and that is the safe wrapper around WebRTC sys. From there, you end up in the LiveKit crate. And the LiveKit crate really encapsulates all of the LiveKit SDK functionality that we were talking about. So all of the signaling and feature implementation that we have in our native platforms, that's all kind of now in one layer sitting in the LiveKit crate. And it calls into the underlying WebRTC underneath. And then, of course, we needed to expose some kind of FFI interface between Rust and the native platforms that we'll build on top of it. And so we have a thin interface there that externs just two methods. The main one to pay attention to here is FFI request. FFI request, you can think of it as a receiver method that is getting protobuf messages from all of the native platforms. And that's how the native platforms are calling into this Rust core using protobuf messages. Eventually, you can see here that we'll be able to export these crates, or rather target them for the WASM, for a WASM build that can run in a browser at some point down the road. And so this amazing work is kind of like a developer's dream. We can now go and delete 70% of the code that we've written, right? Don't want to fall victim to the sunk cost fallacy, right? Get rid of that code. It's one of the best feelings as a developer. And so as part of this, I kind of wanted to take an opportunity to soft launch or soft announce the first consumer of the Rust Common Core, which is something that we've been asked for about a year. It's our most popular request from the developer community, and that is a Unity multi-platform SDK. And so this is an SDK that actually works across every single Unity target that's available and allows you to bring real-time communication into the Unity ecosystem. So here's Theo. It's a silent video. I don't know, he didn't want to say anything in it, and he told me to try to edit out his hair. I don't know how I was going to do that, but here it is. And so he's connecting through our little meeting app. Does a little wave. I didn't think I was going to have to narrate this. And he's going to show off how you can have a live preview in Unity where you move around the camera and you see all of those changes updating in real time, broadcast into a meeting. And then, of course, you can also have layers within Unity that are live. Pretty incredible. Excited to release that to the community later today. Thank you so much. Appreciate that. And I think that, whoa, what the? So thank you for the time and for listening. And yeah, if you haven't tried LiveKit before, would be excited for you to give it a try. You can brew install it, try it out locally, and if you have any feedback, please let me know. And if you build something cool with it, drop into the community. Let us know. We're happy to hear about what kind of things people build with it, and happy to help too if there's anything that you need. Are there any questions? I don't know. Oh, I have 10 minutes? No, I don't know. 10 minutes. 5 minutes. 5 minutes. Nice. That's the first time I've run through this entire thing. So I didn't know how long it was going to take.
First of all, awesome. I did not know about LiveKit. I've done WebRTC stuff before.
Oh, cool.
Oh, hey, sorry, yeah. I was just saying, like, awesome stuff. But basically, first of all, I appreciate that history sort of it. Like, it very much represents like an open source project. One, like that's community driven or like the feedback and so on. And that's awesome to see because like it really put into like it made me understand why the decisions that were made. But basically, I'm wondering. So the part that so there's so many different aspects of it that are interesting, but one of the parts that I wanted to hit on was the end-to-end encryption, which is very important to me and the kind of use cases that I'm exploring. And I was wondering, I have a question of like a use case that I have in mind, and perhaps you can answer like if LiveKit solves that or how you go about it. So having iOS native Swift apps communicating with, let's say, a JavaScript server, Node.js server, being able to send video feeds, being able to send sensor data. These are just two different modalities. Text data, let's say, over, like LLM chat stuff.
Yeah.
Being able to do that, these are 3 tracks, I guess, and being able to have end-to-end encryption on both ends. And maybe, yeah, so is that possible, and is that like easy to do with the current use kit?
Do you answer that, David?
It should be. The whole point about LiveKit is that you have all these different platforms that can seamlessly integrate with each other, right? So you can build, Swift can be publishing and your web app can be receiving, and the end-to-end encryption methods is shared between them. So it should work. Give it a shot.
I'm using WebSockets. I'm using all the different mechanisms for all kinds of different data. I'm encrypting manually, like you would like with TLS, like sort of with it's like a ridiculousness. But this seems to be like incredible. Like I actually worked on this project many years ago now, where we had like a motion capture lab, and we were we were taking, this is like before HTC Vive. We had a project called Vive. Ridiculous. You can never remember it anymore. It was VIE, exact same spelling at Emily Carr University.
Oh, wow.
And we were basically like taking the motion capture data, feeding it into this Oculus DK1 headset that we had made wireless with like battery packs and stuff.
Yeah.
And you would be walking around. And the whole challenge there was like, how do you like do all these different types of data, real time, low latency,
Yes.
all these different things. Of course, and also the second part of that project, the next year was we had a lab in New York run by Ken Perlin, and like a bunch of people like how do you do very, very low latency VR experiences with two different people,
Yes.
2 different labs together.
Yes.
And so we had to explore various different technologies. I'm a web developer primarily, so I always am drawn to like web familiar technologies, and WebRTC was one of the things that I looked at. But I feel like something like this now, at this point, would be an easy go-to, and not to mention the battle tester aspect of it. So.
Yeah, we've been talking a lot about, well, one thing I was going to say about end-to-end encryption is we just released it in JavaScript and in Flutter, I think, into the wild, and now the other platforms are starting to get it too, and that's getting built. So you should be able to do end-to-end encryption across all of them, any kind of permutation that you have between your kind of client and server side support. The other thing that is interesting about what you said is, I've been thinking a lot about kind of the metaverse and VR and how that's going to kind of manifest. And I think for now, in the early days, it's still cameras and microphones. But as kind of VR gains adoption, AR gains adoption, there's going to be other sensors and data streams that you also need to synchronize or transmit over the network. It's entirely possible that I don't think video will go away, because even if video pointed at you goes away, like video pointed outside of the world probably won't go away. So you'll probably still be transmitting video, but there's other types of data streams like hand controls, for example. Yes. Right, all kinds of different things. And so one of the things that we've talked about a lot at LiveKit is kind of tried to build this in a way that is kind of data agnostic from the very start. So yes, there are facilities, because WebRTC provides them out of the box for video and audio, but how do you also handle arbitrary data streams that don't necessarily have the same shape or the same format or encoding? So yeah, I mean, that's also something we're very excited about too.
It's an extremely exciting project. I mean, I came to the talk not realizing that I should have Googled it probably before, but this is
no worries.
I'm going to use it like immediately. I have like a bunch of different sandbox experiments going on where I'm using WebSockets and all these different things, and I feel like I'm trying to figure out each of these problems, which again, as a developer, you get into this mindset, I can solve anything, let's go ahead and try and solve. And I should have just Googled before I got into it, because this is awesome. I'm going to start using it.
Well, we need to get better at appearing in Google too. So even if you Google, you may not find us, actually. No promises.
And the fact that so many big companies are using, which means it's battle test. I think that's an aspect of it. I wonder if you want to have any.
I have a different take on this, but from a project perspective.
Yeah.
I have worked in Web3 with Polygon. So I had worked with kind of metaverse projects, and they were looking at, like, from a developer standpoint, I feel that this is a great solution. But looking from a metaverse project perspective, I see that they're looking for something much more intuitive, which LiveKit, of course, does provide. And one interesting take here would be which kind of metaverse projects are looking forward to this. So I see another use case as edge computing as well, because real-time data is much more important. But from a metaverse standpoint, I'm looking forward to which projects haven't shown interest and how are they willing to develop in.
So I guess what you're asking is the more traditional kind of metaverse projects. So we have a bunch of them. There's a bunch of the more. So again, I think, in my opinion, these are all metaverse projects. Like even robotics is metaverse, right? But I think in the more traditional sense, around, let's say, 3D worlds that you can kind of explore through your desktop computer, but also in VR, et cetera. There are a number of projects there that use LiveKit. So things like Gather is one of them, TeamFlow, which no longer exists, but there's Portals is another one, Decentraland is another one that people have heard of. There's Zep, which is a company that's pretty big in Korea. They use us as well for their kind of world that you can explore and do social activities in. Your question was, how do they use it, or what's the response to it, or?
Yeah, I'm looking forward to it.
It's interesting because it's very use case dependent. So Well, I think the response in general has been positive. One key thing that we heard from the more metaverse category projects or spatial computing, I'll call it that, spatial computing projects, was that a lot of the SDKs, the commercial kind of APIs out there, they're all fundamentally designed for video conferencing, primarily because they were all built, and it's not their fault, it's that they were all built pre-2020. The only thing you used real-time audio and video for pre-2020 was video conferencing. It was Zoom or BlueJeans or WebEx or whatever, right? And so that was the only use case. But post-pandemic, you kind of need this flexibility and this kind of general layer for being able to walk around, bump into people, instantly grab their audio and video, quickly walk away. Sometimes you go into a room and you need permissions around who can access that video. You don't want someone to just kind of like barge in and they actually shouldn't be allowed to get your streams. And so we built all of this kind of stuff into, Gather was actually one of our first customers. And so one of the things that we heard from Kumail in terms of feedback was, well, none of the other APIs support all of these things that you need in a metaverse context, that you need when you kind of think about real time as people walking around, and I need to kind of teleport their presence from outside of the computer into the computer and then sever that connection immediately. So a lot of kind of the fundamental design choices we made were around that metaverse use case. And then it actually ends up being, the interesting part is it ends up being used in different ways by different companies. Even though they're all spatial computing, it depends on how those companies kind of built their metaverse. Decentraland, for example, they use us in a totally different, not totally different, they use us for audio and video, but they also use us for all of their game state synchronization. So like they model the client state of the world, whether an elevator is up or down, whether a door is open or not, they model that as an object on every client kind of instance that's running in the world. And then they use LiveKit as a transport layer to sync that data back and forth. So that's a very different use case that Gather, for example, isn't doing. And so I would say that one of our hopes or design principles was how can we build this in a way that is so generic that you can do any of these things that you want while still being high level enough that you don't have to kind of get in the weeds and understand the complexities of what's happening at like the kind of network layer. So yeah, I hope that answers your question. Any other questions?
I was wondering actually about, obviously the third challenge or the second challenge, like that you talked about, which was the cloud and scaling laterally.
Yeah.
Oh,
That's a second.
Sorry, I feel like that was an important part. And I'm wondering, so LiveKit Cloud, you talked about how it's a massive problem to solve, the idea of multiple cloud providers and in sync in one, and then failure rate being low and so on. I'm wondering, so is that a private offering that you yourself, it's like managed sort of hosting? Is that what that is? Yeah,
so that's managed. I meant to say it. I didn't say it in this version of the talk, but in rehearsals I said it. The thing about horizontally scaling like a network of servers, maintaining 99.99% uptime. One of the things that we talked about. There were kind of really two considerations. One, we're an open source project, so the first thing is that we need to have a commercial offering so that this can be sustainable and we can keep working on it, right? Because we enjoy it, so it would be good if we could, pay the bills. Yeah. So that's the first thing, and one of the first motivations to have a commercial offering. But the second one is that we did think about releasing the code for LiveKit Cloud, but it's just so complicated to operate a network of servers. One, it's very difficult to do, and it's challenging for the team to do internally, let alone someone who's not familiar, who hasn't built this thing and written the code. That's one kind of thing to think about. The second is that most developers and even companies, they don't want to operate the network, right? They don't want to they just want to integrate real-time features into their app and kind of be done with it and think about the next thing to build versus having to kind of drop into this DevOps and SRE challenge of operating this media network. And so, even if they want to, they don't really want, even if they could, they don't really want to. And so that was another reason to not do it. I'm not saying that we'll never, make the source available. But for now, I think there would just be such a huge support burden. Even with LiveKit's open source server, a single server, there's still a lot of kind of permutations into the way how people might deploy it to which cloud with what firewall configuration. When you multiply that to multiple clouds and they're running in different places and stuff, and you have to keep a live network between them and synchronize data between them, it just becomes really intractable. And so for those reasons, it's right now just a cloud managed solution.
So I want to follow up on that because that's a very interesting problem to solve and a very hard one to solve as well. So I appreciate that you worked on that. And of course, if you do decide to open source that, that would be very exciting, and I would be very excited about it. I wonder if I may propose, and I'm sure you thought about it. Managed hosting is still very much a thing that you can have while the code is shared, because like you said, people don't want to do it. Why is WP Engine so popular for WordPress websites? Why is there managed hosting for every single thing? Because people don't, just because you can doesn't mean you should and you want to. I think I'm very big into AI space right now, and I have to, for commercial purposes, for clients that I have, use Anthropic and use OpenAI APIs. But I'm also, for my personal projects, always using all the open LLMs possible, self-hosted and so on. And if I'm going to do any kind of interesting projects that I myself deploy, I would want to have distributed deployment of my own, weights that I have. And so in that case, you would need to solve these problems for other, not even the LiveKit problems, but other problems. And so I feel like there's always those narrow cases where people have those desire to deploy, and though they would appreciate greatly the problems that you have solved there's just the entire, I as a developer, I know the numerous problems that then will pop up as you try to solve it that you have now seen and then overcome. And so they would appreciate that effort. At the same time, there's plenty of people like project managers and everyone else who would not want to manage it anyway and give the liability of the uptime to you to do it. And so on that end, I'm also wondering, are there big companies going to LiveKit Cloud for managed hosting? What kind of customers do you get for LiveKit Cloud?
Yeah, there are big companies. Some of those logos on there are LiveKit Cloud customers, and logos on our website as well. Not all of them, but definitely some of them. Really large companies at scale. Some of them, truthfully, some of them do want some kind of something that they can host themselves. But I think that in general, the market is kind of trending towards cloud and away from on-prem in general.
I mean in cloud, like VPCs and people wanting private.
Private instances. There are some, but I don't think it's the majority. It's definitely some, but there are also, it doesn't look like, it definitely doesn't look like smaller or medium-sized companies are all using cloud, and then all the big guys want to have an on-prem or a private VPC instance of it. There's a handful, I would say probably 3/4 of the bigger companies are completely fine with cloud. Yeah.
And again, on that topic, I'm also interested in that because of for example, one of the companies that I work with, finance baseline, our funding and so on, we have these regulations around data protection and even data at rest, data in flight, how you handle all VPCs, all these database services that we are using. We always have to consider can my AWS cloud VPC work with them and so on. And so I'm wondering if with the managed hosting that because I'm truly interested in a way that I might even end up possibly having to use LiveKit or wanting to use LiveKit Cloud for something. Because if, for example, not just my personal projects, but certainly any client project where I see it going far enough into the multimodal space, I would want that live ability to be reliable. And in that case, I would explore something like this. And so I'm asking from that interest, do you guys have that kind of stuff figured out of the data regulation side of it, and how you manage data at rest, data in flight, encryption, privacy, regulations around it, or is that something that's in the future ahead?
Yeah. So part of it's in the future, part of it's currently there. So like, we know we have SOC 2 for cloud, GDPR, HIPAA will come probably later this year. Maybe ISO at some point if we start to do more business in Europe where they care about that versus SOC 2 as an example. So the compliance side of it is partway through. For kind of like some of these use cases in healthcare or with banks, for example, there is one company that takes LiveKit open source and has built their own distribution of it for banks, kind of these private instances for the 13 biggest banks in the world. And yeah, they care a lot about regulation and where data is and where it goes to. And so for that, frankly, we don't work with any customers there yet in cloud. And maybe the reason why is because it's cloud, right? It's not, we're still a small team, so we haven't gone after that market yet. But I'm sure that with time, when we start to have more of those conversations, it's going to come up. We hear about it already from, for example, from these folks who are doing it in Europe with these banks. So yeah, I think in due time it will come up. But it's always it's one of those things where it's a conversation, right?
Can I actually ask lastly on that topic, is there, so on a simpler level, not again clouds and like the complexity that are involved in the YAML files written for AWS and everything else, like on a simpler level, is there functionality in the SDK for you to be able to set up multiple sort of SFUs and connect them? Is there like that ability in the code base?
You can take LiveKit open source and you can build your own version of cloud.
Yeah.
It won't be easy.
Yeah. But I mean, connecting multiple servers and routing, is that something that you have to manually write on top of it? Like the ability to say, use 3 servers instead of 1?
For a single session, to have a single session map across multiple servers,
yes.
Basically what cloud does,
yeah.
That's something that you would have to build, yeah.
Got it.
That's something, that orchestration layer,
Yes.
that's the one proprietary layer of LiveKit's offering today.
Yeah.
Everything else is completely open source, except for that one piece.
Yeah.
That's something that today you would have to do yourself.
Got it.
Yeah.
Awesome.
LiveKit open source is already set up for you to do multi-node distributed deployments where you can have multiple SFUs around the world, but the constraint is still there that only one SFU can host a single session. You can have many, many, many sessions running in that location, but they always have to map to a single data center.
So yeah, I think that's what I was asking as well. So on a simpler level, you can have multiple SFUs with load balancing, and as long as the same session is on the same SFU.
You don't have to do that yourself. That's completely there already.
Got it.
Yeah, that's completely there. It's just this multi-home versus single home.
Yeah.
That's the one part that's proprietary.
Yeah. Awesome. Well, thank you so much for an incredible talk and the awesome work. I'm going to use this soon. So.
Well, yeah. If you need any help or if you have any questions, just hit us up, and we're happy to chat about it. Thanks so much, you guys. I really appreciate it.